Hi, we're just going to go through the EM spectrum very quickly, starting with radio waves. This radio goes from shortwave radio waves, about 2 meters wavelength, all the way to 10,000 meters wavelength, very long wavelength radio waves. All of those travel at 300 million meters per second. So moving on from radio waves to microwaves, and of course we've got the oven. Now microwaves, good for cooking. They particularly heat fat and water and cause the molecules to do this, resonate and increase in temperature. Waves in here, about 12 centimeters wavelength, the same as the waves that you get in the wireless router up there, but they're less powerful, of course. So that's microwaves, and of course your mobile phone is communicating using microwaves also. We can detect the microwaves with this. So if we switch this on, we can see where the microwaves are leaking out, which tells us we don't want to get too close to a microwave oven for too long. Another way of detecting microwaves is this, which is a klystron. We use this in the school labs. This makes waves which are about 3 centimeters in wavelength. And again, I switch this on. 3 centimeter microwaves. You can't see them, but they clearly have an effect on things. Moving on from microwaves, we've got infrared. And you can see the color of this lamp is very red. Now, of course, the red is visible, but what you can feel here, this warming effect, is the infrared that is heating my hand and will even burn it if I'm not careful. That isn't the visible light doing that, it's infrared radiation. Same warming effect we get from the sun. We can detect infrared, not with our eyes, but with one of these. And if we switch this on, then the camera will show us the temperature of that very hot region. And we can point it at other things as well and see what temperature they are. This lamp also is hot. So that's a thermal imaging camera. Switch that off. Now the infrared, we're talking about less than a millimeter here now for the wavelength of infrared. And moving on, of course, the next one, the shorter wavelength, again is visible. We've got a nice demo here. There are 3 colored LEDs there, which we can turn up and down and turn the blue on and off, and the green and the red, and you can see the effect of mixing those colors. So the visible light is over a very narrow band of wavelengths from about 300 nanometers up to about 650, 700 nanometers. So the red, about 600 nanometers, and then the green, 550 perhaps, and then the blue, around about 400 nanometers wavelength. Getting very small now. Then, of course, we're in the visible, so we can talk about things like eyes. This is an eye. Well, it's a very big version of an eye. I take these lasers, it's got green and red light on here. Let's put some light into our lens, and hopefully I can press both the buttons at the same time. There we go. You can see the light goes into the lens and crosses over. Beautiful. There it is. When I get 2 beams going, you see they cross over there. The lens is converging the light, and it's focusing in front of the retina, which is obviously not good. We would need glasses. So that's visible light. More on visible light. Even though it's a narrow band of wavelengths, we can split it up using the prism, or dispersion of white light. And Newton figured out there's dispersion of white light into that beautiful spectrum there. You can see red, orange, yellow, green, blue, indigo and violet. And this light is already present in the white light. It's just that the prism disperses it because of refraction, and the light refracts by different amounts because it changes speed, slows down inside the glass, or in this case perspex. Do the same thing here with water. Some white light going into this prism, but at the moment there's no water in it. But if I were to tip some water in, then watch what happens on the screen when I tip the water in. Hopefully don't spill too much, and hopefully if I adjust the position of this slightly as well, should be able to get a nice spectrum. Can't quite see it at the moment, never mind. So moving on, we've got, after visible light, of course we've got ultraviolet, get it right, shorter wavelength again. So ultraviolet, where have we got ultraviolet? Right here. And this is a UV lamp. If I switch it on, there we are, you can see some blue light. And the blue light coming out of this UV lamp is, of course, visible blue light, but there's lots of ultraviolet there, which is ionizing radiation. So we'll be careful with this. This stuff's not too dangerous. It's quite long wavelength ultraviolet, but we can, of course, do things like check banknotes. I don't have any of those myself, I haven't got any money, but these will work. These beads started out white, you can see they're now glowing. They're glowing different colours. And the colour is gradually changing as the UV gets to them. There we are, and now the UV has made them into pretty colours. Okay. So that's ultraviolet, used for doing things like getting a suntan or testing for banknotes authenticity. And of course it's a ionizing radiation, so potentially hazardous. Moving on to X-rays. X-ray photograph here, and you can see on this X-ray photograph, there we go, someone's knee. You can see the bones. X-rays don't pass through bones, they pass through the soft tissue, and you can make images of bones and other parts of the body using this technique and reveal fractures or other problems. So X-rays, again, very short wavelength now. X-rays, we're talking about 10 to the minus 14, 10 to the minus 10, 10 to the minus 12 meters, about the size of an atom, size of a typical atom. And then finally, they're of course ionizing as well. And again, the most highly energetic waves of all, we've got gamma radiation, which is very high energy radiation. Again, travels the same speed as all the other ones, 300 millimeters per second. But this one is the most hazardous, the most ionizing. It will knock electrons off atoms and can damage DNA. So again, it's potentially hazardous. This one comes from the nucleus of decaying atoms, radioactive atoms. And again, it's the shortest wavelength of all of them. So we're talking about 10 to the minus 15, even 10 to the minus 16 of a meter, the wavelength of gamma radiation. And again, ionizing. So we haven't got any here because we don't want to get it out when we don't have to. So that's a brief tour of that. And good video to watch to summarize some of this is Bozeman Science, electromagnetic radiation. Short 3-minute video on that to watch.